Thank you for invitation. So actually, I've been thinking why this seminar have not invited me for that long. So I'm very happy to speak here now because you can tell actually what I've been talking today will be this one. Of course, it's an aspect of Gromov's conjectures, but basically it is the opposite of Charlie. It's geometrical, not variational methods to not only scalar problems. Yeah, so I think I should be a speaker of this seminar. Okay, but just kidding. Go ahead. Okay, so for today outline, we have the introduction, and then we'll introduce Gromov's dihedral conjecture, and then we will talk about Positmass theorem, and then if time allows, we will talk about Gromov's thinning conjecture, and if time really allows, I want to talk more about quasi-local mass as well. Okay, so let's start. Let me introduce the scalar curvature. The first scalar curvature, the first curvature we concern is scalar curvature. So how do we see scalar curvature? It's from volume, as by this formula. So basically, we can see that if scalar curvature is strictly positive, then for the same epsilon geodesic ball, then volume of the ball in a metric with positive curvature would be strictly smaller than the Euclidean ball. As you can tell from the picture from a disk into a hemisphere, then you can compute that directly. Then the second curvature we concern is the following, which is called mean curvature, which concerns a hypersurface in the ambient manifold. So let sigma t be a smooth family of surfaces. Well, mean curvature reflects the change of area of the family with respect to unit speed nu. In particular, the derivative at time zero is exactly the integral of the mean curvature. And of course, right, because it's about hypersurface, right, the ambient space and the direction also matters. And after we know those curvatures, then we introduce the scenario of polygons. So in two-dimensional case, we have Gauss-Bonnet theorem. So here, K stands for the Gauss curvature, and then kappa stands for the geodesic curvature, which means the mean curvature. Well, the alpha j's are the interior angles. So let me draw a simple picture here first. Yep. Okay. For example, this is an equilateral triangle. So here, the alpha 1, alpha 2, alpha 3. Now, of course, they're all part of 3 at this moment. Well, on the other hand, right, you can consider equilateral triangle on a sphere. On the sphere, then you can also have an equilateral triangle like this. And this time, all the angle with power 2, and here power 3. Okay. So what makes a difference? And the difference comes from the Gauss curvature difference. So we can tell that's why curvature corresponds to angles. That's the thing we should see. Then from the other perspective, well, given the polygon, if any of the inequality is strict, for example, if the geodesic curvature is strictly positive somewhere, or the angle is strictly smaller than the Euclidean model somewhere, then by the Gauss-Bonnet theorem, we know that sigma cannot emit negative Gauss curvature. So in this sense, right, we are saying that from some C0 information, we can see when the Gauss curvature can be strictly non-negative. Yes. So from this, we may ask the following question. What happens in higher dimensions? And now we can introduce dihedral conjecture. So let P be a convex polyhedron in Euclidean space. A compact Riemann manifold with boundary is said to be of type P if there exists a polyhedral diffeomorphism from M to P. So which means, is there a question? Oh no, okay. Okay, so if there exists a polyhedral diffeomorphism, so which means edge map to edge, vertex map to vertex, face map to face, of course, combinatorially, it makes sense. So in simple terms, right, you may see this as a coordinate chart. Then of course, in general, we can consider more general scenario. For example, degree one map instead of diffeomorphism. So to characterize scalar curvature, Gromov proposed the following conjecture. So given a type P manifold, if it has non-negative scalar curvature, and each face of the boundary has non-negative ring curvature, and then the dihedral angles are everywhere less than or equal to the corresponding ones of the Euclidean model, then it must be flat. So let's see an example to demonstrate it. So here, if you consider like a box, right, in general, every face flat, and then the angle will be power 2, 90 degree. So let me mark it down here first. But this is all 90 degree. Okay. Then what about we blow it up? Right? Because again, right, from the scalar curvature property, effects volume, right, we can tell it become a bigger box. It be a fatter box. And then every face mean convex, right? So we can tell it's like expanding outward. And then you can tell this time, right, the angle, like a tangent line here, like a tangent line here. The angle is already, you can tell it's bigger than 90 degree. So that's exactly what Gromov's conjecture is about. Right, just like here. Again, just do it one more time. As you can tell, of course, we can now see the Gromov conjecture, right, shall be true. But how should we prove this? And let's talk about the progress so far. So but in 17 and 19, right, Charlie has shown the following. Let a dimension between 3 to 7, and then Bernoulli prism with dihedral angles and most power 2, or if n equal to 3, P can be any simplex. So again, as a manifold is type P, then the conjecture holds. Again, precisely. The scalar is negative on the boundary, on the face, right, the mean curvature is negative, and the angle is more than or equal to the model, then it must be flat. And then this by minimal surface approach, and then just as a remark, right, there are some Dirac operator approaches by Brendel, and then Brendel and his student Yipeng, and then there's a paper by Wang, Xie, and Yu, which are also here today. And then let's make an outline of proof first. So of course we may assume the angle to be equal for simplicity for presentation. Okay. So first of all, we focus on the geometric property of scalar curvature. Again, scalar curvature means the volume is being inefficient, so that we're bigger to contain the same amount of content. So which means it must be fatter, as you can tell again from the box, right? So how do we say something is being like a bigger, being fat? We have to look for a belt. Okay, so basically we can imagine the following picture here. Okay, of course the angle cannot be drawn be less than power 2 because they don't exist. But this is a picture here, right? Mean convex being fat. Okay, so now we look for a belt which satisfies the following minimization. So the thing we would see is the following. It is one. It's a belt here. It will be area minimizing. But from this picture, you can tell it does not make sense, right? Because you can tell, right, actually the belly of the fattest part is actually the area minimizer because of mean convex property of the top and the bottom. So we can say something goes wrong, but let's continue. So first of all, on this surface, because we want to do some analysis, we have to make sure it is regular enough. So for geometric measure theory, points of view, we have to use the result by Taylor, Simon, and Edelin, and Charlie himself. And then for some scenario, right, we can use the relativity results of Lieberman to show that the surface here, sigma, is actually C2 alpha. Okay. And then the metric induced on this sigma, right? Because the area minimizer, we can use the first eigenfunction of the following Jacobi operator to do the conformal change on it. And then by tracing all the inequality, we can tell that actually G sigma itself is flat. And moreover, actually the function itself, right, the second function called phi is actually constant. Okay, oh sorry, this is phi to the power 4m plus 3 is flat. And then phi is constant, which means G sigma itself is flat. So first of all, we know sigma itself is a flat surfaces. Okay, this is so far what you have. But then ultimately, right, what you want to show is then the whole manifold is flat, not only the surface. Then what we shall do? There's we have to use the Caloto-Chodos H-Mills perturbation to show density of such flat surfaces. So basically, what they are doing is to say, okay, let's make a perturbation here on the annulus. And then the radius of the annulus can be arbitrary. So it can be very, very small. The key is to say we do the minimization process again. So the new surface will appear along the annulus region. Yeah. Then by adjusting the size of annulus, right? Of course, we have the density of such flat surfaces. And then at the end, right? Let me remove the, okay. So we can tell that from the first version of the second fundamental form, we can tell the Riemann curvature tensor of the ambient manifold actually vanishes. It had been shown first by Simons and Ganglios in their papers. Yeah. So now we know that densely, the Riemann curvature tensor is zero. And because the matrix C2i, which means that really the whole thing, the Riemann curvature tensor is zero and hence it's flat. So this first proof by minimizer, area minimizer, actually tells us the interplay of scalar curvature and the volume in terms of the area minimizer. So it's a beautiful proof. But it is difficult, very technical. On the other hand, right, motivated by Stern's harmonic one-form level set method, actually Xiao Xiangchai has shown the following formula. So the scenario is as this. So let Mg be a cube with all the angles equal to power 2. Then he showed that there exists a C2 alpha function which is harmonic. Moreover, let me draw a picture. T means the top face, B means the bottom face, and then U equal 1 here, U equal 0 here, and then F just means side faces. On here, the normal derivative will be 0 harmonic inside. Okay, so for this function, we will have this integral formula comparison. What's interesting about this formula is that, right, we don't have to assume any curvature assumption. We don't have to assume any mean curvature assumption. So it is by itself true. Moreover, because the angle is assumed to be power 2, then we know that the last line actually will be less than or equal to 0. And hence we have the following. If we assume the curvature is negative, and the mean curvature is negative, then it turns out that the HU tensor here will be 0, which means gradient U is parallel. Okay. Then because for three-dimensional cube, right, we can choose this direction, and this direction. So they occur there are three parallel vector fields which are linearly dependent. So that's why the whole manifold is flat. Yeah. And then there is something we can think about it at this moment, right? For this technique, of course, it is relatively easy compared to the previous one. But then the assumption here, we may try to lose it because the spirits of the Gromov conjectures are less than or equal to. If you force them to be equal to, right, it may be a little bit restrictive at the moment. So we want to remove this assumption. And how can we do it? We'll discuss that in the later part of the talk. Okay. Then let's see another generalization of Gromov's conjecture. So again, by Charlie, say the comparison model is a negative scalar space. In particular, by scaling, we can assume it is comparing to the hyperbolic space. So in a coordinate system, so that GH stands for the hyperbolic metric, express the following form, and assume M this time is a polyhedron model on CO1 on the dx1 coordinate, and then PMS1 on the remaining coordinate, where P itself is a polyhedron where the dihedral rigid conjecture holds. And assume the following. First of all, the curvature is to compare to the one in hyperbolic space. And then for mean curvature, this time the setting, you may see a little bit different. For example, the side face is still mean curvature, non-negative. But then for the top and bottom face, it's a little bit different. It's an M-1 and M-1 condition. but we will see actually we can why this happens later. And then the angle, again, is more than the model one. Then the result is it is really isometric to a parabolic prism in the hyperbolic space. Again, the technique is the same. This time we look for a new base, which is a minimization of such a functional. So I will write in this form because it echoes with what Charlotte has said, right? It's a mu bubble actually in a sense. This time the function is n minus 1. Yeah. And then this time what we have found is constant mean curvature surfaces because the mean curvature will be n minus 1 with a constant, and then also it's a free boundary. And then just make a remark here for Chai and Wang, they use this technique to show the corresponding rigidity result holds for general class of polyhedra in 3-dimensional, including simplexes. And then for Chai and Wang, this is not typo, they're very different people. Wang and Wang, yeah, Chai and Wang, they use a Dirac operator approach to show the corresponding results in a high dimension as well. And it is a very good trick, a very clever trick on Brendel chart. So now we have enough knowledge about Gromov's original conjecture and some tweak. So now I'm going to give you what I promised, right, as a title and this perspective of the conjecture. So first of all, let's consider this one, X and T. It's a Minkowski space. And then what is Euclidean space actually? Actually, just any space-like plane, any space-like plane. It can be this one, it can be this one, it can be this one. But any space line is Euclidean space. Then what is hyperbolic space? Actually, it is the hyperboloidal equal 1 plus x squared. Okay. So what we have done so far is to say, given you a polyhedra, a compact set, can you put them into a particular part of Minkowski space? Okay. So say, can you put this here in the hyperbolic space, or can you put this into here in the Euclidean space? So in this sense, right, we want to ask the following question. Then what about, can we put it here in other part of Minkowski space? Or can we put it here? Right? Or to curve it like this? Can we? The question is, can we? So now we have to introduce the concepts of initial data sets. Okay. So given Mg as a Riemann manifold and K is symmetric CO2 tensor, then why do we call them initial data sets? Because this free tuple is actually the initial data sets for the Cauchy problem, which is to construct a Lorentzian manifold which satisfies the Einstein equation, which means we want to construct space-time. So here, let's draw a picture. Here's an Mg Riemann manifold. And then with respect to, if there is a space-time y, there's a time-like unit normal, n. And then with respect to this n, y, you have the second Van Hoff form. This denoted by k. Of course, right, Mg has to be isometrically embedded into the n bar g bar, the space-time. Yeah. So that's it. So it's a Cauchy problem. That's why it's called initial data set. Okay. So now let's fix some notation. So first of all, for seminar form, we define this way, and then mean curvature will be the chase of the H. So that's why we have the outward pointing normal, right? For sphere, you will have positive mean curvature. And then sigma is called minimal surface if the mean curvature congruently vanishes. And now because it's take K into consideration, right? Again, that's why I didn't erase it. I put it here. K is the sigma form with respect to time like normal. So if K is taken into consideration, sigma is called a marginal outer Cheb surface. If H plus K sigma K is congruently vanishes. Corresponding, right, H minus K sigma K equals 0 will be called marginal inner Cheb surface, MIDS. Okay, so what is the meaning? First of all, It is the time normal here. It tells us information about 3 sigma k. And then for the space-like direction, right? We also have a nu. We have h. Okay. So what if h plus 3 sigma k equals 0 mean? Altogether, direction along the direction of this diagonal, which is a light. Of course, a now direction. Yeah. Which means the area cannot change at all. Which means there's so much gravitational force or attraction so that even light cannot escape. So in physics, right, we call this surface apparent horizon. And then at the end, right, let me introduce one more notation. There's a pi tensor. This is called conjugate momentum tensor, which is the tensor k matrix k times g. And we'll see this in the next slides. We'll mention it very often. So now, given initial data sets, we can define the mass density and current density as follows. So 0 here means the time-like normal. So mu is T00, and then J is a T0, the vector. So the dot, right, means direction in the tangent of the manifold M. So dominant condition is satisfied if mu is greater than the norm of J. Then at this moment, you may say, oh, do we need the whole space-time information to write down mu and J? It turns out, luckily, no, because we have a Gauss equation and Kodály's equation, we can express them completely in terms of M, G, and K itself. So this is a formula. So mu is a scalar curvature with some terms of the extrinsic curvature K, and then G is the divergence of pi. So that's why pi is defined this way for rotation simplicity. So now after we know initial data set, we know the energy, then we can think about how shall we formulate the question about how to embed a compact set into Minkowski space. So first of all, if you consider mg0, which means it's time symmetric, just by direct computation, we can tell that the dominant energy condition, DEC, corresponds to non-negative scalar curvature. And say dimension of 3, right? If we see hyperbolic space as the MGG set of Minkowski space, then we can tell that scalar curvature bigger than or equal to -6 because we're talking about dimension 3. Okay, actually corresponds to, again, dominant energy condition. And of course, right, for MGK in general, we shall expect the condition we assume on the initial data set shall be dominant condition. And then we may think about, okay, we have some idea about the condition we should assume, but then how do we prove it? Well, as we can tell in the beginning, right? Charlie used a minimal surface and then constant mean curvature surfaces. So what are they actually? So we can tell the minimal surfaces is actually chase zero of the extrinsic curvature K. And then CMC surfaces actually chase sigma of the G. Again, the extrinsic curvature G. That's why we expect we shall have a foliation of a moss or mist. But then the question is, right, how to produce one? Because for the previous one, right, again, minimal surfaces or the constant mean curvature surfaces, they come from variational processes. But then for moss and mist, they do not come from variational methods because itself is anisotropic, right? For example, I fix a point, right? I can have this one, I can have this one. Even though they happen at the same point, right? Then the trace sigma k, sigma 1k, and trace sigma 2k here. It's different. It's anisotropic. It cannot be coming from a variational problem. So this issue is an obstacle that we have to overcome if you want to prove something. And then moreover, right, we can tell from the hyperbolic space scenario, the boundary condition is a little bit more complicated already than the original Euclidean model case, right? Then how should we formulate it? And now I have to introduce some more physics terms as follow.
I have a quick question. Can you go back?
Okay, Oh,
When you say it is not from a variational process, do you mean that it's not known to be a variation of any sort of energy, or that it's definitely known not to be?
uh, according to my reading of H. Mayer's paper, I would
Mm-hmm.
say it's definitely not coming from a variational problem.
Okay, thank you.
Yeah. So for Hamiltonian formulation, what is it? Okay. So let omega gk be a compact initial set with boundary sigma. Picture. Oh, maybe I should draw it here. Yeah. Omega here, sigma here. Then we can construct a space-time by saying we flow it along this direction. Right, then the boundary is called sigma bar, and the whole cylinder, right, the whole thing, the whole tube is omega bar. Along what direction? There's a Vn plus W. A V is a lapse function, and W is a shift vector, which is tangential to omega. So altogether, we call it partial T because it's like a proper time. Okay, and N, just to make sure, N means time not really normal. Okay, so we flow along this, then we have a space-time, right? Then we can say the purely gravitational contribution to the total Hamiltonian at the slice omega is given by the following quantity. So mu and j here expected. And then on the boundary, oh, we can tell something, which is h and the pi nu one form. Okay. So just to remind you, right, what is pi? Pi is a conjugate momentum tensor. And to make our life easier, right, let's see some example. Say we are considering time symmetric case. Actually, it tells us that if we say the v is 1 and the shape vector just zero vector, which means it's just always just make a flow along the vertical direction. We can tell actually the gravitational Hamiltonian actually comparing the scalar curvature and the mean curvature. Okay, so the example. And this one now in general, we know what we should expect. And this is the following. Okay, so dihedral conjecture for initial data sets, which are exactly not only scalar curvature. Yeah. Okay, so let MGK be initial data sets of type P, which satisfy the following. First of all, in the interior, the dominant condition is satisfied, and then the boundary dominant condition is satisfied. This time has to be H greater than the pi nu, the one form. You can see from here. Okay, and then we also assume that everywhere the dihedral angle between two faces of M is less than or equal to the one of P, Euclidean model. Then we expect MGK can be isometrically embedded into Minkowski space. So now we successfully formulate a proper conjecture. Then in the following part of the talk, right, I will try to say, okay, some partial solution of this. And then motivated by Stern, of course, I will say also by Witten and Pagatash, right, because as the spinner perspective, right? And then Hertz calculates curvy proposed space-time function. And you can tell, right, for space-time function, what does it mean? It's Laplacian U plus trace k times the gradient U equals 0. It's a function here. While for the Dirac-Witten operator, right, we also have the so-called harmonic spinners. There's a Dirac operator, and then minus trace k is a potential. Okay, so you say they are in the sense parallel. So first of all, this is a following lemma. So this time I don't have to assume it's a cube. It can be a general prism, just any, for example, even you have a dodecagon times 0, 1. Okay, as long as all the angles are are smaller than pi, then there exists a non-negative space-time order function, which is a very ugly regularity. First of all, the angle, because I just have to be smaller than pi, right, it can be varying. Right? For example, you can make a nip here in the box. So it will be smaller here, is bigger here, smaller here, bigger here. So the angle is not constant. That's why the regularity, as you suppose, is very ugly indeed. Again, the top is 1, the bottom is 0 for this function, and then for the side faces, it's a Neumann. Okay. And then just to introduce this method, right? The Stern's method. So there are 4 key ingredients, but I will skip this because it's just a bunch of computation. but you can ask me afterwards. But the key I want to mention is the red one here, this one. How do we see this method actually? You can tell that's why, because on the level set of the U, spherical level set, that's why good manifold, good submanifold. So for the normal here will be gradient U, the one normal gradient U. And from this, we can tell directly, right? It is a normal direction nu. We can have a second power form. And the good point is, this second power form actually is a Hessian U, the one normal gradient U, which are the tangential sigma. So this is very useful. And we'll see it. How do we use it? Again, we skip the computation. Okay, now we go to here. So by integration by parts and Courant formula, we get the following thing. So first of all, mu and J shows up. And then the Gauss curvature of the level set shows up. Then say if we have the Gauss-Bonnet theorem, then we should be able to tell the angle of the level set, which gives us the information of dihedral angles. So this is a good equality. And then indeed, it is very useful in the following form. So again, let MGK be of the prism type. Moreover, this time, again, it can be a hexagon, just whatever, right? This time the angle, they can be quite greater than pi over 2. But as long as the angle between the top and the side faces and the angle between the bottom face and the side faces is more than pi over 2. Right, less than pi over 2 here, less than pi over 2 here. Okay, let's say not equal to pi over 2. Okay, then we can have this result. You can tell again the angle assumption comes up because of Gauss-Bonnet theorem. And why do we need this extra, the highlighted angle assumption? It's because of the following. We do have to show integration by part makes sense, right? Because if you remember in the beginning, right, actually the regularity of the U is so bad. There's only W12 and W3P away from the edge, away from the vertices, and then by the Georgian dash mosa, right, it's C0 alpha. So it's a natural question to ask, or how can this make sense, right? Because you have the Laplacian and then normal gradient U into the free derivative. Okay, and that's why it is difficult. And the key is following, right? We have to do it bit by bit. So for the face, for the vertices, for the vertical edges, right? For these vertical edges, this might, okay, for example here. Well, these are the vertical edges. And then actually, but more interesting point is the horizontal edges, which means this one, the horizontal edges, right? The horizontal one. Because interestingly, right? If the angle is every power 2, everywhere power 2, right? Then it is C2 alpha. The function is in C2 alpha up to the vertex, up to the edges. But then if the angle is everywhere less than power 2, it's C1 alpha. Interestingly, if there's sometimes power 2, and then sometimes more than power 2, and sometimes greater than equal power 2, right? Then actually it is C01 Lipschitz only. Classical differentiable, but may not be even C1. So that's why we have to use a broad argument. And then we have to use some boundary Hahn inequality to tell us that even though it is not C1, but the integral makes sense along the horizontal edges. Okay. So say after we overcome those difficulties and we really get the formula, then what do we observe? First of all, under suitable energy and angle condition, right? For example, you assume something on mu and J, you assume something on HM, the pi nu tensor, and also you assume something on the angles. Then we should expect this time what we want to be 0 is the following tensor. This part. This is 0, as we highlighted here. So what does it mean? Which means the second level form of the level set with respect to the space-like normal and the time-like normal altogether is 0, which means it's a totally space-time geodesic modes. And then it will be a foliation because a function where the level sets foliate the prism. So each mode is actually stable. Then from this point, we can already use some result by Anderson-Mark-Simon, Galovic, and Carlotto on stable modes to have some geometric results. And then just to make sure, because we are talking about modes with boundary, so that's why to be more precise, I have to use some result by Ali, Lasut, and Yao on stable capillary modes. And what is a stable mode? So basically, it's just the same as stable minimal surface, in a sense that we just have to do the first variation of the function that we concern. This time h plus j sigma k, and then if this operator has a non-negative eigenvalue, then this is called stable. I'll just skip this because it's a long computation. Okay. So now, first of all, we can talk about comparison theorem. So let MGK be initially a set of a prism type, again satisfying all the angle assumptions we have discussed before. Then if you assume the dominant condition, we go in J, and then this time the mean curvature assumption is a little bit funny. You can tell h greater than the chase of k on top, chase of the bottom k on the bottom, and h on the pi nu only eating the tangential part. Then why is it the case, right? And now I have to introduce one more idea. There's a following. And there's some novelty about the condition. Here, again, the top and bottom. Why is it a single observer condition, right? First of all, we consider pi nu tensor, a pi nu one form of the say. Then on the say we have a focus because characterized in Calculus space. There exists a parallel observer. So I assume there's a parallel observer in this direction, in this direction, in this direction. Maybe I should use other color. Give me one more. Okay. Then what does this pi nu eating, right? There's a pi nu negative nu, which is exactly negative chase k on this face. It chase bottom k, not negative. And here, right, is a pi nu eating some tangential direction. Okay. And that's why I have this assumption 2 and 3. So this is called boundary dominant condition by a single observer. Yeah. That's an introduction of some new terms. Okay, but what is the result, right? First of all, just by the integral formula, we can tell that, right, the diagonal angles of M cannot be everywhere less than those of P. Yeah. And here, EJ means the vertical edges. Again, here, say for example, here, there's E1, E2, E3, and there's E4 are the vertical edges. Okay. And then we can talk about further on diagonal rigidity. Okay. First of all, on this page, right, I don't have to assume the angle is more than or less than equal, less than or equal to the one Euclidean model. I don't have to assume that. They just follow from the integral formula. But now we have to separate the picture diagonally, right? Because if we further assume the angles are everywhere less than or equal to those of P, then we have the following results. First of all, mu would be equal to J on M, and then all the assumption on the boundary, right, inequality become equality. And then the all the diagonal angles will be the same as the Euclidean model. And this I have to point out, right? Actually, of course, by Gauss-Bonnet theorem, you may expect, okay, we can always get some information on each slice. Right? For example, you can tell this is power 2, power 2, power 2, power 2. Or you may expect this. But actually, from the regularity of the harmonic function, we can tell actually this angle is also has to be power 2. Yeah, so it's an interesting point of view analytically. It's more than the Gauss-Bonnet theorem itself can give us. And then again, just every set, right? For every level set, then totally space-time geodesic. And by stable Morse property, right, we know that each level set is actually isometric to the two dimensional polygon up to some scaling. So up to this here, right, actually, we have some results already. First of all, is the existence of foliation of Morse under a single observer, DEC. Yeah, because if you compare the results here, right, to the one say by H-Mail, Anderson, Simon, right, they always have some H greater than or equal plus or minus chase sigma k. So in the sense that, for example, on a sphere, right, sorry, on a ball, right, let me tell like a wave. What is chase sigma k? Again, chase sigma k is pi nu nu. Okay, so this nu itself form a whole family of observer, but now only one observer. say pointing upward, one observer. So it's an interesting result in that sense. And then we have some rigidity results already for MGC or MGG using the Watt Porter formulation here. And of course, I mean, for the time being, right, I will skip this. We can come back in the Q&A session. But again, I can tell, right, we can tell MGC or MGG directly from the level set method. But then, again, what I promise, I at least have to give you a partial solution, right? Because if I just talk about MGC or MGG, then I'm just doing the thing that Charlie have been doing. So what is the novelty here, right? So indeed, we can really put some compact initial data sets into Minkowski space. They may not be Euclidean, they may be hyperbolic, just somewhere. And that's formulate the theorem. So first of all, in the interior, the dimension condition is holding, and then the boundary dimension condition is satisfied on each face, and we have to assume the diagonal angle is less than or equal to pi over 2. Then indeed, it can be embedded into Minkowski space. Moreover, the boundary is actually isometric to the boundary of a Euclidean rectangular prism. So as a corollary, we get this. So actually it comes from example constructed by Gromov. So let MGK be initial data set of cube type. The MGK cannot simultaneously satisfy the following three conditions between domination condition, boundary domination condition, while all diagonal angles are acute. It's just impossible because if the case K equals 0, right? Again, Professor Gromov has already constructed the example. That is impossible.
Mm.
Okay, so now let's go to the proof. First of all, actually, again, by the same idea of this cube, we can always choose 3 or even 6, right? 6 directions. So by symmetry, we can tell that the second Mayoral form of M, I mean of the boundary M with respect to M, boundary M, right? This second Mayoral form nu is a vanishes. And then the K tensor restricted on the tangential part is also vanishes. Moreover, the pi nu tensor, the whole thing is actually 0 by symmetry. And then again by the property of stable modes, because now each 6 faces are all stable modes. That's why they're scalar flat. So between Gauss flat, they're really flat. And then because we can choose 2 different directions, right? Then we can tell from mu equal to j eating this direction and j eating another direction. So by some ODE argument, we have that mu equal to j equal to 0. So up to this moment, we can already conclude for a cube, it's a vacuum. But vacuum is not enough, right? Because for some of such shells, it's also a vacuum. How can we ensure that it is really in Minkowski space? So now I have to introduce some other concepts. This because I tell you, right, the partial solution are by Posey-Marsh theorem. And now I'm going to tell you what Posey-Marsh theorem is. So I initially said MGK is called AF. If outside of a compact set, it is going to be flatter and flatter and flatter. That's why G goes to Euclidean metric, and then the extrinsic curvature tensor will go to 0. Okay. If we further assume mu and J is integrable or manifold, then we can define quantities called ADM energy and momentum. You don't have to remember the formula, but basically, what does energy mean? Detecting is the change of the metric itself at the sphere of infinity, while P, the momentum, is exactly measuring the momentum tensor at infinity. Okay. And then just as we remarked, right, Bartnik and Crucial, they prove the division is actually independent of the choice of the coordinates. As long as they're simply flat, it's okay. And what is Posey-Marsh theorem? That's following. So at least 3-dimensional. Let MGK. Oh, wait a minute. Sorry. There's some technicality issue here. I cannot remove the notation. Okay, but skip it. Okay, done. Okay, let MGK be a initial data set, which is a simply flat. So if the dominant condition is satisfied, then E will be greater than normal P. Moreover, if equal P, then equal P equals 0. And MGK is actually a slice of Minkowski space. I'll just have simple look at this theorem. So let's go back to the time symmetric case. We forget the K, just say K equals 0. It's a classical theorem that we see more often. But what is so special about it, right? First of all, we can just say R3, just take our compact set and then take a metric in this form. Then our scale should be 0. And then the ADM energy would be the parameter M, but not the M can be arbitrary. So what's so special about here, right? And actually, there is some tricky point. Because if M is negative, right, the manifold itself cannot be complete. So that's why it's a tricky point. And actually, as a simplifier itself, right, is assume the completeness already. So that's why this problem will not occur. But it tells us that actually, apart from the physical energy, right, there's something called gravitational energy that we have to consider in terms of physics point of view. So this theorem has been proved by Xin and Yao in 1979 and then written like 2 years later by a Dirac operator method. And then I just want to highlight two, which is Bartnik and Jasiewski-Kijowski, right? Actually, they have proposed using harmonic function to prove Poisson theorem already in the 1980s. So it's interesting, right? Yeah. And then of course, I have to mention like the method by Stern, like a Bray-Curry Stern and Hertz-Curry. Yeah. So now I want to introduce Poisson theorem with corners. But because you may say, oh, why you suddenly, right? You're just considering a cube, a box in your hand, but why do you have to consider the whole universe suddenly, right? As a simple fact, why? And we will see. They are breached by the following theorem. So let's say for a simplified manifold, right? And set is the following. They have an inside, I call it G minus K minus, outside G plus K plus. They respectively move up to the boundary. And then this boundary itself, right, needs not to be smooth. It can be a piecewise smooth surfaces. And then say outside is more flat, and then G is Lipschitz across the sigma. And moreover, say I have some topological condition. And note that K doesn't have to be continuous. They just have to be smooth inside, outside, and they can just be bounded. Yeah, so they can have discontinuity indeed. And this is a beauty of this field. Okay. And then there exists a space-time function such that the following holds. And in particular, the last line, right? If we assume the energy condition on interior, on the boundary, on the boundary sigma, and if E equal P equals 0, then we can tell M is indeed topological R3 and can be isometrically embedded into R31. And just as a remark, right, because some people may say, oh, then this looks so similar to the proof by Witten or Parker-Taps on Poisson theorem, and of course with some tweaks of the regularity, right? But what's so special about this is that we don't have to assume the condition mu and j and h and pi to ensure the existence of harmonic function, right? Because you remember, right, for harmonic spinor, you have to assume the energy condition is satisfied, so that you have the Fredholm property, so that you can have the existence of harmonic spinor. So there's a slight difference. Okay, but now go back to the question, right? How we can really show the cube is in Minkowski space. Okay, just recall the three properties that we have discussed before. And because we know that's why, this time the six faces of the manifold is indeed isometric to the one Euclidean space. Then we can just patch it with Euclidean space, just patch it as follows. And then because of the property I highlighted, right, the blue one and the red one, right, we can tell that the energy condition is all satisfied. Moreover, of course, Euclidean, right, outside, right, so E must be 0, P must be 0. And hence, the whole thing must be Minkowski space. In particular, the thing itself is Minkowski space. Yeah. And just as a remark, Charlie mentioned that by Locam's commodification method, right, that actually dielectric rigidity implies Poisson theorem. So this time it turns out the same for the initial data set. Okay, because we also have the log-chem complication. But actually, again, just a side remark, right, we don't have to use log-chem technique. Actually, we just have to use a density theorem, like a conformally harmonically flat, then it is enough. And then moreover, right, for the diegeometry, actually holds for prisms for single observer, DEZ. Because actually we can turn, it tells us that if we have a foliation of modes, like in three-dimensional scenario, if we have foliation by modes, then you can just follow from Gauss equation, Kodazi equation, that actually the space-time, if it can be embedded into, must be flat. So it is first done in a paper by Yip, like in 1980s, in using spinor. And then recently you have like a rewrite, or in a sense like a reproof of the theorem by harmonic space harmonic function by Spenhurst and Zhang. Yeah, but basically Gauss-Kodaly equation. So actually not the diegeometry only for cube, but also for prisms in general. And I have to mention that's a development proposed by Brendel and his student Ewan Chow. Okay, so now we want to talk about more on geometry, because some people, again, we are not working on general relativity, right? But what's so special about this technique on geometry itself? So again, as Charlie has mentioned, right, soap bubble, milk bubble is with prescribed mean curvature H, which usually obtained by the minimization process. And then if one lets a K tensor to be this tensor, H thereby M minus one, again, H is a prescribed function, right? G is the metric. And now, of course, there's a folklore in the community, but it's first shown in the literature by Lee, Lassu, and Unger. Then in the case, right, actually, we can get a foliation of sub-bubbles by the level set approach. So again, for example, for standard Watt products, right, we can tell Gill, Hong, and Curry, and Hurst, Castles, Curry, and Zhang, they use this method to have a foliation of milk bubble, which compared to the original variational method by Jin Tianzhu and Hu Liuxi in some problems on scalar curvature. Yeah. So actually, in this perspective, right, we can also see when prism can be put in the structural space-time, because structure is also Watt products. We have some special property of the mean curvature. So actually, this can also be done. Yeah. And you might be a appendix in my update on my paper. Okay, but then actually, okay, let me see if I have enough time. Okay, I can finish one more part of the talk. Okay, so for boundary interior geometry, let us see for the Gauss-Bonnet theorem. So here we can tell that if the Gauss curvature is everywhere non-negative, then we can tell that the integral of the geodesic curvature must be bounded. Or on the other hand, right, if the Gauss curvature, geodesic curvature, point-wise sense or integral sense is being too large, then the polygon itself, the two surface itself, right, cannot admit a non-negative Gauss curvature. Then again, we shall ask the following: what about high dimensions? And this is a Gromov filling conjecture. So let Mg be a compact manifold with scalar curvature, which is bounded from below by some constants. Sigma can be negative, can be positive. Then there exists a big lambda depending only on sigma and the intrinsic geometry of the boundary, such that the integral of the mean curvature must be bounded. Yeah. So this makes sense again by the Gauss-Bonnet theorem. This completely makes sense. But then so far there is no really a full solution. And first of all, let's see the conjecture in a physics point of view or general relativity point of view. Again, we go back to here, the Hamiltonian formulation. So we can tell that mu and j is in the interior, h and the pi nu one form is in the exterior. In the boundary, boundary, yeah. So this time, not only comparing scalar curvature and mean curvature, we should be comparing the h and the pi nu, the whole thing as yeah, on the integral. Okay. So let me introduce a concept called bucket data sets and fill in. So sigma, gamma, alpha, h, and beta is called space-time bucket data set. Say sigma, gamma, alpha is an oriented, closed, null coordinate initial data set. And h is smooth function on sigma, and beta is a one form on the tangential of sigma. So what is a fill-in? So a compact initial data set is called fill-in of the data set if this is isometry of the sigma to the boundary of omega, such that the mean curvature is indeed the function we prescribed in the beginning, right? This h. Moreover, the k nu on this one, when you put it back, is a beta, and the chase of k would be the chase of the alpha on the boundary. So there's some partial solution in the following sense by Xu Zhu and Xu Wei, and of course also by Mel. In the following sense, they're saying that if the mean curvature is being too big in the integral sense, on pointwise sense, then given a data set, you cannot fill it in with a non-negative curvature. And also there's some variation. Again, because of the Hamilton formulation, we may expect the following conjecture. So that is, let MGK be a compact initial data set where the energy is bounded from below by some sigma. Then there should exist a constant such that h minus pi nu, this whole vector integral, I mean the norm of this vector, would be more than equal to lambda. And this is some of the partial solution. Of course, there's some variation in terms of integral sense as well, but I just put one here for presentation simplicity. Okay, so again, so we have a space-time bucket data set, and say it can be embedded in R3, and then the metric this is smooth by smooth surface. Then there exists a constant such that if h minus f, again, f here just means a pullback of the pi nu norm. So in a sense, if the energy is leaking too much along the boundary, then inside you cannot have double energy condition, right? Because it's so physical, right? Again, energy is leaked too much away from the boundary already. Then inside the energy shall be negative. And actually, right, there's a recent extension of the result. So fill-in can be complete non-compact or with an energy shield in the sense of a Lee, Unger. And actually, this improvement is by a recent proof of a post-mass theorem, arbitrary ends by Sacchini, Lasut, and Sidor. Yeah. So actually, we can not only consider compact fill-in, we can consider complete fill-in as well. And then just a Walut, here's another perspective of DEC spin fill-in by using the first eigenvalue estimate of the Dirac operator to show the non-existence. Yeah. And then let me see. Okay, time is almost up. And I think I have 2 more minutes. So let me go to this part, the angle part. Okay. So here. So for polygon, we call the Gauss-Bonnet theorem. After rearranging, and just say for simplicity, again, the other characteristic is just I mean this is one, then we arrange this one. We can tell that the integral Gauss curvature equal to the negative of the integral geodesic curvature and the angle difference. Well, alpha bar j, right, means the angle is back to the Euclidean metric. So again, the same question. What happens in high dimensions? So here, angle deficit as a localization of mass is first done by Mel in a 3-dimension, and then by Mel and his student Anna Piobello. Then they have this formula. So as long as it's flat and then PK be a sequence of Euclidean polyhedra going to infinity, then they have this formula. So you can see exactly like this one. Just kappa the geodesic curvature with the mean curvature. So it's a higher dimensional generalization. Okay. And then this interesting here is that the polyhedra need to be convex. And that's why corresponding, right? Actually, we can consider the initial data scenario. So if we assume that the simplified initial data set satisfy double condition, and then this time let PK be a sequence of Euclidean polyhedra going to infinity, and norm of A is 1, then we have this following formula, which is the limit of such the integrals would be non-negative. And this is done by Positmass theorem because double condition is satisfied. And this will actually converge to E minus P. Yeah, so it's a direct generalization of Mel's result and Mel Piobello's result. Okay, so to sum it up, So today we'll be talk about like C0 characterization of the dominant condition, which is again definitely not only scalar curvature. Again, from boundary interior geometry, we can talk about fluiding problems, and then we can tell that the relation of a cube and the whole universe. So we can see as a localized mass. Of course, we talk about ADM mass itself. Yeah. So that's the end of my talk. Thank you so much.